Hello everybody, welcome back. In this lesson, we will go over methods of logarithmic differentiation. We are already familiar with the derivative of natural logarithm function. That is none other than, if you recall, it is just the derivative of ln of x. That happens to be 1 over x. And this fact will be used in this computation, but that is not the most important aspect of it. That is one key component that you need to have in your computations. But now, to prepare the background for these computations, let me just provide the background. First of all, this new topic, this particular topic, logarithmic differentiation, when are we going to use it? If you look at the upcoming examples, when you endure through all of those examples, you will recognize one important aspect. We use all of those computations when you have tedious multiplications or divisions in our derivative computations. Or there is another aspect you will see by the end of these computations when you have somewhat complicated functions, especially in terms of variable powers or variable exponents. We will use this method. And I will elaborate both of these directions in upcoming computations. But first of all, let's look at required tools. These required tools, these tools are none other than exactly the properties of natural exponential function and natural logarithmic function and the connection between those two. First of all, to begin with, the first property is none other than the inversion of the exponential through ln, because this works since we define ln as the inversion of the exponential function. And then the second property is a computational property. When you have a product inside ln, you can break it into a summation. The price that you need to pay would be having ln in front of both of those terms. But this will be significant in our computations because it's always easy to take a derivative of a sum compared to a multiplication. The same thing would go with a division. If you have ln together with a term divided by another term, inside ln if you have a divided by b, then that can be converted to a subtraction instead of a division. So this could be substantially simplify. This could substantially simplify a given problem, because other than using the quotient rule, you are granted to use a linearity property. Only knowledge that you need to have would be the derivative of ln for each component. And then the last but not least, it is the power, right? So when you have a power inside an ln, this is common with every ln aspect, right? For every ln, every logarithmic term has this property. You can bring this power to the front of that term, leaving just the base inside the computation. So all of these are, in fact, all these last three properties would be valid for any logarithm function. However, the first one is tailored for natural logarithmic function in particular. And in calculus, we will pay attention only to natural log function other than working with any other basis. And that would be sufficient. In upcoming conversations, I will show you why we do not need to look at other bases. Now, a blanket assumption in these equations, whenever we have an input in an ln function or a logarithmic function, we need to make sure that the input is non-negative. Otherwise, the computation or the argument or the function value will not be defined. So it is a blanket assumption, and I'm not going to reiterate it again and again in our upcoming computations. I will just have it by default as an assumption. Now, let's look at this example. This is most likely an example that we have already seen. This is not surprising. You can do this computation in two different ways. Method number one, you can use directly, just for this derivative computation, you can use directly the chain rule. So you can say the derivative of ln of x is 1 over x, where this whole thing is playing the role of x. So 1 over, put this whole thing, and then times, you're going to do the quotient rule together with the product rule for this component, and it's going to be a headache. But if you do not buy my word on it, please go ahead and just try it and see it for yourself. But now what I'm trying to do in this occasion is, without going in that direct computational direction, I would like to do this computation by employing the algebraic properties of ln. So my starting step is going to be not the differentiation. I'm not going to take the derivative, I'm going to hold it. So I will leave d by dx in front. And then I will use the algebraic properties. Now don't forget, this square root is none other than a power of 1/2. So when I take this ln, this is how it would look. I have x squared plus 1 to the power of 1/2, and then plus ln 3x plus 5 to the 10th, minus, don't forget this is in the denominator, therefore it has a minus in front, because when you have a denominator, you're going to subtract that term when you distribute this ln. Now, x squared plus 1 raised to the 3. Now you can do this, or you can do it even conveniently, other than writing these pieces, these powers here, and sparing one more line to bring them out. You can simply say, all right, let me just bring the power to the front, because we know that is one of the properties. So I will do that after buying a little space here. Can you see? You can do this in one single step rather than spending too much of effort or another completely different line for this computation. In other words, you can do the logarithmic simplification in one single line. And once you do that, now you're going to have an amazing time with the computation, because it is going to be so easy. Now, none of these log terms can be simplified any further, because those are having additions inside. When you have a multiplication or a division inside ln, you have an amazing way of simplifying, but unfortunately it does not have anything when you have an addition or subtraction inside. So now let's take the derivative. When you take the derivative, this is going to be the derivative of the first component and the second component and the third component, and they are just combined by additions or subtraction. So 1/2, which is exactly this factor, times 1 over x squared plus 1 times the derivative of the inner function, which is 2x. Don't forget, I utilized the chain rule in that case. And the same thing that I'm going to do here. So the derivative of ln 3x plus 1 over 3x plus 5. In that case, the derivative of the inner function will result none other than just times 3, and then minus 3 times. Now the derivative of the last component, 1 over x squared plus 1 times 2x. And that is pretty much our final answer. Now, there are a couple of things that you could have done. In this case, I had this like x square plus 1 in both places. That means you can simplify it further. There is an untrivial simplification for that, right? Uh, so there is a trivial computation for that. So you can do that. But now look at this. Pretend that you were about to take the derivative of this function by using the direct method. Pretend that you are at the beginning of the computation of the functions, the inside function, which is exactly the quotient that you're seeing. How easy would it be? But look at this. When you utilize the properties of ln, you got to the answer in just 2 lines. You're done at this point. Now, there are simplifications that you can do. 2 cancels with the factor 2 here. You can combine these 2 to get 30. You can combine these two terms and say like it's 6x. You can do all of those, but those are not really necessary. That is just simple kindergarten level algebra that we would not worry about. All right. So let's proceed to the next level. Now, the previous example being example 0. Now we are looking at example number 1. What is the difference? Here I am saying, here I am asking you to take the derivative of this component, this function. Uh, the only difference compared to the previous problem is not having an ln. So in other words, we are trying to take the derivative of this quotient right away. We can use the quotient rule directly. Of course, we can do that, but that's exactly the obstacle that we had in the computation previously, right? So that is exactly what we're trying to see now in this occasion when we do not have ln. In the previous problem, we had an ln right in front of this function, and that had amazing ability of simplification of this problem. But now we don't have it. Now, when you don't have it, what are we going to do? Are we going to use the plain version of logarithmic differentiation or like just the quotient rule? Maybe not, right? We do not need to go with the regular method. Let's try to do this computation in a different way. Now, just to make did not disappear. That's fine. Then we can just leave it. Okay. What we need to do is to take this derivative, right? To do that, now I'm not going to do it directly. Instead, I'm going to show you the real idea of logarithmic differentiation, and this is how it's done. Now, log differentiation. This is step number 1. You do not need to write them like step 1 or step 2. I am going to just put them in parentheses so that you can organize your understanding. Step number 1. First of all, I'll grab the given equation as it is, and I will take ln of both sides. So ln y. So when I take ln y, when I put ln on the left side, since this is an equation, I need to put ln on the other side. Now look at this. This has no calculus. I'm just taking ln of both sides. Why do I do that? Wait and see. You will see the reason in a moment. So when I take ln of the right side, now once we have ln in front, we know that we have that amazing simplification of separation and taking the powers out. So we will end up getting this. If you do not see exactly how, just recall exactly what we did in the previous computation, right? So that's none other than minus 3 times ln of x squared plus 1. Now, we do have this. And the next step will be the computation of the derivative. Now, when you compute the derivative, don't forget you have this left side and you have this right side. The left side has a function of y. So that makes it an implicit differentiation problem, but an easy one. When you take the derivative of the left side, that becomes 1 over y times y prime, because it's a function of y. In the right side, you will end up getting the derivative exactly that you computed in the previous example. So that will be just 1/2 1 over x squared plus 1 times 2x plus 10 times 1 over 3x plus 5 times 3 minus 3 times 1 over x squared plus 1 times 2x as the derivative of the inner function. Now, here we have the answer for y prime, but not only for y prime, it comes with this 1 over y term in front. So let me cross multiply by this term, just by y. So I will get y prime equals y times, right? I will just write y. And you do not need to write it like y. In a moment, you will see y. Let me show you. As a placeholder, I will just put it like y. I multiplied by y. So it's right there. Times, and then the first term. Now here I will simplify. 2 goes with 2 and just make it 1 over x squared plus 1. And these two will combine with each other to make a 30. So 30 over 3x plus 5. And here you have 3 times 2x, which will construct a 6x. In fact, you can see like these two terms are getting associated with each other. You can have that simplification because of that ignorance in our problem to make it look better. But look at this. This is the real computation where the derivative occurs, and then the rest is pretty much algebra. Now this y is none other than what you have right here. Therefore, just copy this right hand side and paste it in the position of y. So I will literally do that here. I will just copy and I will just get rid of this and I will just paste it right there. That is our final answer. So step number 1, I forgot to have this steps. I started saying step number 1 here. Step number 1 is taking ln of both sides. Step 2 is basically taking the derivative of that equation right away, which involves implicit differentiation. Step number 3 is none other than cross multiplication by y. So when you have y appeared in the right hand side, you already have the answer for y prime on the left hand side. So y prime is sitting on the left side. Whatever appears in the right side, this entire term is none other than the answer for y prime. Now in this case, you had to use 3 steps. That's all. When you use logarithmic differentiation within 3 steps, without a painful computation, you can get to the answer. Now, let's look at one more example. Example number 2. In this scenario, I do have this function. Here, this is x to the 4 plus 1. So in case if it is hard to see, this is x to the 4th. And then with logarithmic differentiation. Now, since we are familiar with the method, you can pause the video and give it a try. Now, my approach for this particular problem is to show you the answer with log differentiation and without log differentiation to compare these two scenarios. All right, so give it a try. Pause the video and give it a try. First with logarithmic differentiation, compare it with the previous example if needed, and do the computation and see whether you can reach the answer. All right, I hope you gave it a try. Now, let me start exactly with the first step. I'm not going to label them. I will just do the computation right away. First step is to take ln of both sides, and I will simplify the right hand side at the same time. So it becomes 10 ln of x for the first term minus ln of e to the 5x will be just 5x. That is none other than the very first property that we saw in our list of properties, list of tools that we had right at the beginning of this lesson. And then, okay, so this is not a minus, it should be plus because both of these terms are in the numerator and these two terms are in the denominator. Therefore, you will have a minus in front. So minus 3 ln of x plus 1, and then square root is power of 1/2 ln of x to the 4th plus 1. Now, this is what we have. Now, in this case, in this computation, if you do not see how we got just plain 5x here, think about it. It is none other than just taking exponential, taking ln of this exponential. So since the bases are the same, that will result just 5x. The exponent could be recovered. Now, in the next step, once we have this simplification all the way to the ground level, what we're trying to do is to take the derivative. Take the derivative of the right side. Take the derivative of this component, negative 3 times 1 over x plus 1, and then take the derivative of, oh, a quick correction here. This should not be plus, it should be minus. I will put it in the red color since it's a correction. So this should be minus, and this should be minus. Both of those terms are sitting in the denominator. It's going to be a minus, and then 1/2 1 over x to the 4th plus 1 times 3 4x to the 3, because the derivative of x to the 4, that's 4x cubed. Now you can simplify. F prime is none other than, after the cross multiplication yields exactly this term. And then you will open parentheses and you will write exactly this term, preferably in the simplified form. 10 over x plus 5 minus 3 over x plus 1, and then simplify, that will give you just minus 2x cubed. This is what we have. The derivative of f is going to be what you see here. Most importantly, you had to spend like less computationally painful 3 lines to get there. Now let me show you what happens if you do not utilize log differentiation in this. This is not a terrible example. Even in that case, you can do the computation, but you may need to endure somewhat a computation. Now let me just grab this one. I will copy it and I will paste it. What I really need is to take the derivative. To take the derivative here, I can take it directly, but look at this. Look at the computation. We need to have the product rule right here. right? We need to have the quotient rule to begin with. It is a quotient, a function divided by a function. But when you need to divide the function, the top function, which is like playing the role of function f, we need to take the derivative with respect to the product rule. So 10 x to the 9 e to the 5x plus x to the 10 e to the 5x times 5. Now look at this. Pay attention only to the derivative of this component that has so many moving parts. And then multiply it with the original denominator. The original denominator is nothing other than what you see here. Now this is only the first half of the numerator of the quotient rule. And then I'm not going to even try the rest here because I know I will run out of space. Therefore, I will just jump to the next line. Now I need to do the reverse of this computation. First of all, I will have this one fixed. X to the 10 e to the 5x times the derivative of this component that has 3x plus 1 square. That's the product rule again, multiplied by x to the 4th plus 1 plus x plus 1 cubed. The derivative of this component is none other than 1/2 x to the 4th plus 1 to the negative 1/2 times 4x cubed as the derivative of the inner function. Now this is just the top of that computation. And then in the denominator, you're going to have x plus 1 cubed square rooted with x to the 4 plus 1 and the complete square of that term. Now, this is just the answer. Of course, I wrote it in one single line, but can you see it cannot be fitted into one single line? And there were multiple computations in this scenario. Multiple computations. Some of them, like by any chance, if you had difficulty in seeing how this computation was performed, you need to go ahead and try this and see. Now think about the scenario when you had like more than just only 4 terms here. There are 4 different terms, 2 at the top, 2 at the bottom in the function. If you had like, let's say 10 pieces at the top, 15 pieces at the bottom, are you going to follow this method? It is difficult. Definitely it is tedious. So that is why I told you this computation has tedious moving components in the process. But when you look at logarithmic differentiation approach, it is much more neat and it is tidy. And then if you see a difference of the final answer, it is none other than it is subject to just a simplification, and it cannot even be seen in this scenario because it's already complicated. Right? So try to understand the difference between these two approaches. The direct approach can work, but when you consider indirect approach, it has much more flexibility, right? The logarithmic approach has much more flexibility and it is tidy. All right, so let me show you the scenario. Now, in previous example, we had 2 different approaches. We can use the direct differentiation or you can use logarithmic differentiation. And this is a scenario you cannot avoid logarithmic differentiation at all. Now, let me compare this problem with something closely look familiar, but not exactly the same. If you had x to the 10, we know we do not have any struggle. We are going to have the derivative just like this, 10x to the 9. That is the power rule. But look at this. That is not what we have here. We have 10 raised to the power of x, not x raised to the power of 10. The key component behind the power rule is to have a fixed exponent at the top. It should be a constant. However, in this scenario, we do not have the luxury of a fixed exponential or exponent. So in that scenario, what are we going to do? So look at this. This is what I'm going to do. First thing that I'm going to say is this. That is not going to work. Or in other words, you cannot use the power rule. If you were thinking about the power rule for this problem, it's completely incorrect. Don't do that. When you have a variable power of a function, the power rule is not going to function. So instead, this is what I'm going to do. I will pretend like, let's say, first thing, I will look at this function. And since it's not given like a y equals something, I will write it like y equals something. Y equals 10 to the x. Now, what I need to do in the next step is to compute the derivative of y. If I have y prime, we are done. Now, to do that, the next step, first of all, I will take ln y. I'm not going to take the derivative right away because I have no clue how to do it. But I do have a way when you take the derivative of ln. When you take the ln of given function y. So when you have it, this is what it's going to be with the simplification in the right side. Now take the derivative at this step. When you take the derivative, it happens to be 1 over y times y prime. In the right side, this is a constant. ln 10 is a fixed value. There is no derivative involved with that. So ln 10 has it's just a constant multiple, and then take the derivative of x. That would be just 1. So the answer for y prime is none other than y times cross multiply by this term. So y prime, y is none other than 10x already. So I will just put it there, 10 to the x, and then ln 10. That's our final answer. So if somebody asks you about this, that's none other than the answer. The final answer is now along the same path. If somebody asks you to compute, let's use a different color because we can prepare a formula out of this. If you need to take the derivative of a raised to the power of x, where a is any positive base, where x is of course the variable of differentiation here, the answer is going to be a to the x times ln a. Why did you have, like, when you consider ex, when you take the derivative of ex, of course that is just pretty similar to this one, right? Why did you have just ex? In that scenario, you had ex. If you follow the same formula, you have ln e, but don't forget ln e is none other than just 1. So it happens to be just ex. So if you see this, if you look at this general structure, you can see you can work with any base. The derivative of any function, any exponential function with a different base can be handled in this way in terms of derivatives. Now, let's proceed with one more example to see the real potential of this scenario, right? You have even variable in the base and a variable at the top. What are you going to do? Let's follow exactly the same method. First of all, I'll take ln of f of x. In the right side, when I take ln, the power comes to the front. So x square ln x plus 1. And now you take the derivative of the left, 1 over fx times f prime x. In the right, it becomes just the derivative of this product, plus the derivative of the inner function here turns out to be just 1. It need not to be written separately. Now cross multiply by f of x. F of x happens to be just exactly the term that you see right here in the function. So x plus 1 raised to the power of x square, open brackets, and have everything here fed in that. So ln x plus 1 plus x squared divided by x plus 1, and that's our final answer. So in this way you can handle any power. It need not to be a constant exponent, it could be a variable exponent, yet you can use this method, and this is the only method pretty much. There are different variants of this method, but it's essentially involving the natural log function no matter what. So one last computation. Now let's do this problem. Now given that, provided that we are already familiar with the setup, now you should be able to pause the video and do this. This is going to be the last problem of this lesson. So why don't we go ahead and give it a try? All right, I hope you gave it a try. Now let's do this. Let's take ln of y first. Ln y. In the right side, you have a product of two pieces, and both of them are involving variable powers, but that doesn't really matter. When you use this method, it is consistent, right? X times ln of x squared plus 1. Now take the derivative of left side, 1 over y prime. In the right side, when you do this, don't forget ln 5 is a constant multiple multiplied by the derivative of x plus 1, which happens to be just 1. So the answer for the first part of the derivative is going to be just ln 5 times 1, ln 5. The second component has a product. It's a multiplication. So 1 times ln x squared plus 1 plus x times the derivative of the component is going to be 1 over x squared plus 1 times 2x. So y prime is now going to be cross multiply by y, and that's going to be just exactly the same function that we began with, 5 to the x plus 1 times x squared plus 1 to the x. Within parentheses, I will have, within brackets, I will have all of these terms. ln 5 plus ln x squared plus 1 plus x times 2x will result 2x squared, which is divided by x squared plus 1. And that's our final answer. There is no further meaningful simplifications that we can suggest in this scenario. So with that, we conclude this lesson. Some of these computations could seem tedious, but you need to understand what's behind it. If you understand exactly the meaning of the computation and how it can simplify our problems, then it becomes a whole lot easier to proceed with these computations. And then try to summarize. In this case, we deal with complicated combinations of products, multiplications, right? Products, that means, in other words, multiplications and divisions and complicated powers. Or sometimes these complicated powers could even be variable powers. That's exactly when we are going to use logarithmic differentiation. The method of logarithmic differentiation which can help a lot in simplification and differentiation. So with that, we will conclude the lesson. We will meet on the next one. Uh, let's see, with more exciting topics in calculus.